This is going to be a shorter version that somewhat overlaps with the tutorial from Tuesday, but also contains content that was not covered in Tuesday, mostly like Outlook stuff. So what's happening next, which seems to be, you know, it's for some of you might be very interesting. Cool. Okay, so we'll do LLVM OpenMP. Let's see how much content I get through, and at some point I'm going to skip to the end to talk about Outlook and things that are currently in the works and soonish in the works. This is, you know, one of those overview slides. I shared the link for the slides in the chat. You might want to grab it. You might want to take a picture or find it somewhere else. You don't have to remember all of this. But nowadays, it should be very simple to download LLVM and get an offload-capable compiler built. It's like one CMake command and a make command. So we simplified that quite a lot. Couple of good options here, but you'll find all of this in the slides. This is more interesting. This is a summary of the things you should take away from current support. So things that we added over the last year or so that, like since the last time we met at IWAM, that are important to people that do LLVM OpenMP offloading. So stay up to date. I mean, we're constantly evolving and fixing bugs, improving performance, and so on and so forth. So stay up to date. Like a week-old version is okay, but if you come to me with an LLVM 14 bug, I'm going to say reproduce it on main. Otherwise, I don't care. I don't have, you know, I can't keep up all the old stuff. It's really go with nightly compilers. Optimization remarks are key. If you haven't run optimization remarks and you're like kind of wondering about performance, you've done something wrong. First thing, like run OpenMP optimization remarks and see what they tell you. They have online documentation. I get to that later. That online documentation describes them. That says, hey, here's an example. This is what this means. Is it good? Is it bad? Here's a way to, you know, try to get away, like change your code to get the bad stuff gone and get better performance and so on. Optimization remarks, really great. And then the other thing is, if you want to know about how the GPU code is executed at all, run this libom target info thing. It's always available. It will tell you when is data mapped, why is it mapped, what is the current, you know, status of the mapping table, what are the variables that are like data transferred, how much of them, what kernels are executed, in what mode, with how many threads and blocks, and so on and so forth. All the good stuff. Profile gives you like a Chrome profile tracing file that you can, you know, visualize. It's kind of a poor man's always available profile tool. If you really want insight, go with one of those professional tools that people develop. This is really, it's built in, it's easy to use, and it gives you kind of an idea. So sometimes this flags stuff. So it's like you see, oh, update takes all of the time. What's going on? It's not going to be, I mean, we'll improve it, and we're going to add kernel profiling soon, like in-device profiling as well, but it's always going to be very basic. libom target debug is a two-way debug mechanism that allows you to do, by default, it's disabled and you have zero cost. And if you enable it, you will start paying for it. And that allows you to do runtime assertions, common assertions about common problems that may appear, like you run out of heap memory. Because the result of running out of heap memory on a device was probably going to be a seg fault. And if you just see a seg fault on, you know, your report, you don't know what's going on. But if you turn this on, it might tell you malloc return a null pointer. And at that point, you have an idea what's going on. And you can actually increase your heap memory and stack memory through environment variables with LLVM OpenMP. So you can actually control that. We have a lot of performance like assumption flags, runtime, like environment variable or compile time to help the compiler. We hope to get rid of them eventually while the compiler is, you know, smarter and better and so on and so forth. But for now, some of them are necessary because we just don't have the analysis. Some of them will always be necessary. So take a look at those. I'll have them later again. They can really help your performance, and most of them you can set all the time. People usually don't violate them, but I can't just enable them by default because the standard, I would violate the standard. So I don't. And then device offload LTO. Offload LTO is great even if you do not have multiple translation units or you just don't spread your code across multiple translation units. We are actually going to very likely make offload LTO the default. And then you don't have to set it anymore. We might actually remove the support for anything else. So you can't unset it anymore. So let's see about that. Oh yeah. If you have any questions, go and ask the community. Those people don't bite, most of them. And if you ask them virtually, they will not bite you for sure. There's various ways to get in touch: mailing lists, which are now forums, IRC, discourse. Go to the webpage of LLVM. There's a lot of good links there. Getting involved is a great start. LLVM 15 has been released now. It comes with various improvements towards LLVM, OpenMP offloading. So we're looking at a new driver, which allows you to, which exists for OpenMP and it's used by it's the only driver used for OpenMP offload. We removed the old one. It can be used for CUDA and HIP as well. And if you do so, it makes CUDA and HIP compatible to a degree with OpenMP offloading. So you can mix CUDA code, like you have a CUDA device runtime that does, random number generation from years ago. You can link it and call it from your OpenMP target offloading and so on and so forth. But you have to use the same driver because the driver will determine what is the embedding, how is, stuff put together, how it's linked together. Multi-architecture binaries, you can build a single executable, run it on various computers, like architectures, multi-sub-architectures, and so on. LTO, I mentioned, full support for static libraries. And when we say static libraries, we obviously mean static libraries that have offloading code in them. So all ways you would build that and use that should work now. I mentioned interoperability and on the performance flags. So this is my usual slide of I'll get to that later. Right, as of right now, no. But with our downstream stuff, we can make that work, yes. And we're working towards upstreaming that, but yeah. Lots of people involved. I'm just giving the talk here because I have a pretty face. That's the only reason. So everything, like a lot of people are actually working on this, and I'm just a messenger. Again, a slide with a lot of links. You obviously can't, type them up now, but the slides are available in the chat and you find them otherwise. Go for these things if you're interested. You can just listen in to these meetings, or you can present your work in these meetings and ask for advice how to, get it into LLVM, or just advice on how to solve problems. We'll try to be friendly. And then people that actually came to us and worked with us closely got something out of this. This is the performance flags for the full OpenMC app that does OpenMP target offloading as their main programming model. OpenMC is a full nuclear reactor code thingy that they developed. And when you look at so there's different things they did, optimizations, and they got speedups from them. And when you look at these numbers in the circle on there, those numbers are basically optimizations they got by working with, the OpenMP community and changing either their code or identifying problems in the LLVM OpenMP implementation. And once we kind of fixed all of those, we got, quite a nice speed up overall. And the CMake Unity build is basically what we used before we had device offload LTO. So that, and with offload LTO, we get the same speed up, but we don't have the same compile time explosion because we can do the LTO only on the device where we need it, not on the host where we don't need it. So that's what a good change is here. Okay, as I mentioned before. So this is kind of a little bit older, but if you enable -G or -G line tables, you now see, source locations with error messages, which is kind of cool. And an error message mentions, oh, here's a web page that has more information. We mean it. So try to go to those and complain if they're not good. If you have things like libom target info, it's a bitmap. You can use it to get information out of the runtime while the program is running. Here, it tells you, about implicitly mapped arguments, which is something you can't otherwise really know. I mean, they're implicitly mapped. So you see, hey, this argument was captured a certain way, and so on and so forth. So we can provide you with that information. And if you enable like -G or -GD line tables, you actually get variable names and source line information and so on and so forth. So all of that should work. And then there's this debug stuff, as I mentioned earlier. You get some cool stuff like, oh, malloc returned a null pointer, and afterwards your program crashed. So you actually kind of have a good idea why it crashed. There's a couple of other debug flags, and we're adding more as we go. And if you have ideas, please reach out. Oh, yeah. This is the way it is implemented, just for the people that are curious how this can be zero cost, because we have a single runtime, and there's no multi-runtimes. You don't have to switch. You don't have to set anything. Command line flag makes it possible to completely eliminate it if you don't use it. Okay. Allocators. The GPU allocators kind of work. I mean, 2 of the 3 work, and the third one is going to work. Though for us, given the way we currently do implement, like lowering C group and P streams is effectively kind of the same thing. We can't make a real distinction. It's probably that may or may not change in the future, but that is what it is so far. So you can write code like this, where you put a buffer into local shared memory, like the same as you would do with __ shared in CUDA. And you can put this integer flag here into thread local memory, which it wouldn't be placed by default, because you take the address of it, and then you might share that variable between different threads. And if you do, we have to put it in global memory so that to make that possible. But and we try to undo this globalization later on, but we might fail. And if we fail, you get a remark, and that remark says, "Oh, we failed to deglobalize the variable at this location here, and maybe you want to do something about it, like allocate it explicitly in thread local memory." And then you get fast code. It's great. We have these extensions that are now, I think, standardized, all 3 of them. So device memory is just, device global memory. Shared memory is what is often called like managed. And host memory is host pinned memory. So we heard about this earlier, and you can use the extension names, or we'll obviously adopt the standardized names, and either way will work. And we have this one thing that is kind of not fully baked out yet, but it's a cool feature. In CUDA and in HIP, you have dynamic shared memory. At the kernel's launch time, you can say, I want that much memory, like shared memory, that is, shared between one block. And in OpenMP, you can't. So in order to port some applications, we built in basic support for that. Right now, the support is per app. So every kernel gets the same amount of shared memory, not per kernel launch. And it's a fixed amount. So it's not perfect, but we're working on making it per kernel launch. And then you use this funny LLVM on target dynamic alloc shared function to get a pointer to it. And then you can use it like any shared memory. The optimization remarks. We have these 3 remarks categories in LLVM. So you can access them through clang, through these 3 flags. And after the equal sign, you put in for what paths do you want the remarks. So you can basically enable it per analysis or per transformation. In this case, for OpenMP, the path would be OpenMP minus opt. So OpenMP opt, and but you can also run it for loop vectorize, and then you get vectorizer remarks, right? All OpenMP remarks are going to end with omp and a number. That way you can, identify them online and go to the web page that corresponds to that number, and then read up on what they mean. It's not, we didn't come up with this idea. People did it before, but it's actually a neat concept. on the remarks, we just have a single line. I mean, we can't really print much text. So that is the way to give you an idea. So how does it look? So you should run your code, you run the remarks, you read the remarks, and then you act on it. So tells you something about floating point reordering, and then you can say, hey, it's safe. Trust me, I don't mind. Just go with recognition. Similarly, it might tell you, you have this local variable here, and you pass the address to this function that we don't know anything about. And then you get this funny remark that says something, okay, globalization didn't work. Maybe try something out like no escape. There's others. And then online you see, on the web page, you see examples, you see explanation, what is the problem, what's going on, what can you do about it. And this is how the web page looks. And at the beginning of the web page, there's also further links to the remarks infrastructure in general, because the remarks you can use profiling data to filter remarks, only the ones that are in hot regions, so ignore all the rest, and so on and so forth. You can save the remarks into YAML files, as seen yesterday with the Intel folks, and then inline these YAML, like basically create HTML files that have your source code and the remarks next to them, and then you can hover and see what's going on. You can use the Pharos tool that we built a few years back to overlay different versions, like with OpenMP and without, or with certain assumptions and without, and see the different remarks, the difference in remarks, like kind of the difference, and so on and so forth. So there's a lot of stuff you can do with remarks, and I'm not going to much more detail. Assumptions. So you have these remarks, and the remarks might actually tell you something. Hey, we couldn't do something. We need information. Well, it's like compilation is about static analysis a lot, and static analysis is somewhat limited, and sometimes we need help. And assumptions is a good way to help us. There's three main ways to do assumptions right now. We introduced OMP assumes into the standard, and we actually use it. Like we implemented most of it, not all. And we use it for certain things. It is actually implemented basically through the second interface, which is attribute assumes, and you can just put anything there, and it will be attached. And then if an optimization, knows what that assumption means, it's going to, utilize it. And command line flags. If you just grab for all the FOpenMP flags, you will see what is currently available. I'll show it in a second, but it changes over time. So this is a good way to update it after a while. You don't have to wait for me to give another talk in a year. So those are the assumptions we have, more or less. The few that are standardized in 5.1, a couple of extensions that we added for mostly to work with the runtime. So we actually utilize these extensions in the OpenMP device runtime, but some of them we also have added for the user to be able to act on remarks, so that the remarks become things that tell you what to do about them. Like, here, this is what you can do, and then we'll do the good thing. And then below there, you see all the OpenMP assumptions for command line. And finally, nowadays, we have the first environment variable assumption, which will turn off the atomicity of map clauses. So map clauses, as per standard, have to behave like they're atomic, but there's a lot going on. I mean, you copy stuff and it takes a while, and so on and so forth. And for the longest time, we didn't actually implement them properly. We just didn't, they didn't act to the outside observer as an atomic thing. And nothing broke for the longest time until someone came up with this test case where something broke. So most of the time you probably will be fine without this atomic stuff. So, and it can cause cost. We have seen apps that actually, have to pay cost because of it. And so if you don't need it, which is very likely the case, and we can talk about it, you can disable it. And there's other things like that will come up in the future where we're like, okay, we have to do it right. We give you an escape hatch because I don't know what else to do. Okay, execution models. We heard about generic and SPMD mode earlier, and as Deepak kind of alluded, SPMD mode is great, generic mode isn't. kernel programming languages just run SPMD mode, so all the threads run all of the kernel. Here's an example with a CUDA function kernel launch. For the function func, 1 block, 4 threads. That is how it kind of executes. And if you have OpenMP code, you have this, conceptually sequential parts where the team main thread executes and then a parallel activates these threads that come out of nowhere and then they go away and so on. And obviously that what is happening here on a GPU, those threads do not go away or come, like you can't create them. They exist somewhere. So you actually have to make them do stuff. And in SPMD mode is the upper one, which is good. So if you see remarks about we moved something to SPMD mode, great. If you see remarks about something, oh, we couldn't and it stays generic mode, not great. It's not the worst. It can still perform fairly fine, but it's certainly SPMD mode is faster. Why is it hard to move something into SPMD mode? I mean, the generic idea, as Deepak mentioned, is to guard code and then, execute with all the threads and guard all the sequential parts to be just the main thread. It sounds pretty simple and, kind of is, except when you have in the sequential parts other things like nested parallel regions. Now, the behavior of that parallel region would be completely changed because only one thread encounters it. And now, the other threads are waiting at that barrier and you can't really get them back to that parallel region. So it would be sequentialized. Or even worse, you have a barrier in that sequential part. And now you basically broke invariance and guarantees by OpenMP. So things can go wrong. So we'll do our best to make it to get into SPMD mode, but we can't always do that. And if we can't, we emit a remark. We try to point what the problem was, and you guys can help us. But we run SPMDization by default as an optimization. As soon as you run 01 or so nowadays, it will run and try its best to do it since like a year or so. libom target info tells you about execution, if it is generic or SPMD, so that way you can find out also at runtime what's going on. How is generic mode implemented? It uses this, state machine. So whenever you encounter a parallel region, you tell all the workers that are waiting in a state machine on a barrier, hey, this is the parallel region I encountered. Go execute it. Those guys are going to execute the parallel region and tell the main thread, how we're done, and then they go back to waiting. So that's roughly what is happening. So if you ever heard of the state machine, or we optimize the state machine, which we try as well, that's what's going on. That's what's happening. Okay, device libraries, libm, libc, libc++, all of those good ones, right? Initially, you have none on the GPU. They are not there. I mean, there is no library that you link against, just this. Historically, math is kind of where we started. What compilers did is they lowered it to these device math functions right away, early on, usually in the headers, like early on in the compiler front end. And then the vendors provided implementations for these math functions, and that's what happened. That has drawbacks because LLVM knows what a sign is, like a sign function is, but it doesn't know what an NV sign function is. And that actually can cause performance regressions. We've seen, I think RSBench or so got 20% faster once we left it to be a sign function, because it could hoist it out of some loops by knowing that that function actually, is not bad. And the implementation of that in NVSign actually has state. They do lookups, they do like all sorts of corner case handling. It's really hard to argue that this is, easily hoistable. So wasn't. We have a device math library, basically a libm for all the GPU architectures. We're about to, upstream it, and then that will be linked in, and you get the best out of both worlds. We're working on libc function support for the device. We have like roughly 10, 15 implemented for on the device, and then we're working on ways to do RPCs in a good way to get the host to do the others. That's roughly what it will end up with. We're going to hear a driver linker talk later. Joseph is going to talk about it. Quick notes, we have, the new driver comes with a new linker setup. We have a linker wrapper that allows to do device LTO in the first place. That was not possible at all before. It basically, unwraps the object files, grabs the device code out of them, but also the LLVM IR, does LTO, links everything together with the vendor tool chains, puts it back into the executable. Cool features that we got in the driver are deduction of triples. So if you just specify the sub-architecture, it will deduce the triple for you. So you don't have to write minus XOMP target equals MVPDX64 anymore. You can just write offlog SM80. And it also many architectures at the same time. So you get an object file that has both GFX 90A and SM80 embedded in it. You can use the object dump, LLVM object dump with the offload flag to actually analyze these object files and so on and so forth. So you can see all the offloading images. What is this built for? We have LTO. And then if you do static libraries, also always should be supported. And if you have a static library, with 64 different architectures embedded in it, which is actually how we ship the device runtime nowadays. And you then compile, you link against it, but you only require, one architecture. We'll only extract that one architecture. It will do smart things, the good things you need. So all of this is, actually pretty nice. You can, here is a way to build these kind of device libraries that have all these architectures embedded, and then you can link against them. And if you turn on device LTO, you basically get zero overhead. It's actually optimized once the library is linked in, which is great. CUDA and OpenMP interoperability, and HIP and CUDA for me are kind of the same thing, except that we have to sometimes duplicate efforts. But we put the new driver also now into the CUDA, into the HIP toolchain. So if you enable a new driver and enable the RDC, you can call CUDA functions or HIP functions from your OpenMP and the other way around, which is great. You can't really share global state right now because that's really complicated, and we don't yet know how to do that. You can share pointers and so on, like malloc pointers and stuff like that, but not global variables and so on. That's not the thing yet. So you can compile only for the offload device, mostly for if you want to analyze the IR and see what's going on. You can also disable the host fallback completely. So we don't generate host fallback for target regions. Has the benefit that if your target region contains calls to device only functions, you don't have to provide, sham host headers that don't do anything. So if you really have say, okay, I have to offload this to whatever my devices are because it's device functions that I call, I don't have to provide like an empty host version of it. You just disable the fallback. Okay, linker wrapper stuff. I'll just skip through these because we're running out of time and I want to have questions rather than anything else. We have a virtual GPU as to offload to debug stuff on the host, which allows you to do, GDB on your target regions or Valgrind or stuff like that, heap summaries on your code. And it reuses all the device infrastructure. So it's really close to what would run on the device, exactly the same runtime. It's slow, but it's good for debugging. Never supposed to be fast. If you want a fast offloading of the host, do something else. LLVM OpenMP device info is a neat executable that is built automatically. You run it. It tells you what LLVM sees currently as devices and information about those devices. So it lists them all and says, oh, I see this GPU, that GPU, and this host thingy, and here's a couple of key data about it. It's just good to get an idea what the OpenMP runtime sees, so you don't get confused. We have the target profiling. I mentioned that we're working on kernel, like device profiling, and then the data is embedded into the host profiling into data, and user-defined profiling. You can say, hey, start region, like start profile here for region foobar and stop profile here for region foobar, and then it shows up as like a function foobar in your profile there. So you can, profile certain loops or whatever you want to do. It will never be, super great, but it will be like the easy, fast, the dirty solution for people before they have to pack out, like go for big. Remote OpenMP offloading, you probably heard a lot too much about it anyway. Intermediate layer. Okay, this is kind of cool. I'll spend 2 minutes on it. This is the OpenMP, LLVM OpenMP offloading toolchain. OpenMP goes in, device and host compilation. We put a lot of things into the device compilation, embed it in the host, and run it on different things. We will support Intel GPUs. We will soonish have a math runtime. But what we now did is through the new driver and embedding scheme, you can combine CUDA and HIP code with OpenMP. And what we added now, which is not upstream yet, are API and built-in wrapper layers. Effectively, what it allows you to do is to run CUDA code on the OpenMP runtime layer and make CUDA code portable. You can then, once they translate CUDA APIs to OpenMP APIs. And once you're there, you can run them everywhere that all the platforms we support, including AMD hardware, soon Intel hardware, and the host through the virtual GPU, for example. So this is unmodified CUDA code running the virtual GPU on the host, set a few breakpoints, look at a few variables. So you can run CUDA on the host. You can also run CUDA on AMD hardware, and I'm not going into too much detail, but the long story short is it actually is fast. We are as fast as the native programming languages. There is the regular OpenMP runtime offloading overhead, but I've never in any real app seen that show up as a problem. The only time we're not as fast is Lulesh on AMD, and that is because our AMD offloading plugin doesn't support streams yet. We do not have any implementation of a stream abstraction, and that's why we lose out performance there. Once we add that, we get faster AMD performance for OpenMP programs, but also for the ones that come from CUDA and use streams or come from HIP. Then we currently have this prototype. Usually you have OpenMP and you run your OpenMP program on the host and then you offload to the device. Nobody really specified that is the way it has to happen, right? Take an OpenMP program from 20 years ago, there was no offload. Just has, OpenMP code and parallelism. What we can do is we can turn this around. We take this old program that doesn't have offload and we compile it in its entirety for the device. Run it on the GPU. The main function of the user program starts on the GPU. And we run it there. And if we encounter something that has to that we can't do on the GPU, we do RPCs to the host and go back, like fopen and so on and so forth. We have that at LLVM HPC if you want to learn more about it. The initial prototype works fine. It's just really bad in performance. It's really slow. Because we only run on one team at most. And we run the entire program as one kernel. So the register count is up the roof, and we never get much parallelism out of it. So what we did instead is, instead of a parallel 4, we have analysis and transformations that split a parallel 4 in the original program into a separate kernel that runs on all the teams. So we now start, you encounter in your original program a parallel 4, and we start a new kernel that runs now on the entire GPU. For the offloading part in certain proxy apps, we already match the performance of the manually offloaded stuff. The initialization part is slower, but at the end of the day, we're working on this. This will be cool. Where next? Okay, we're running out of time here. We'll have library call support through host RPC. We automatically make things or increase asynchronous execution. So we have a paper at LLVM HPC for some of this already, which is a runtime-based approach. And you have to enable it because it has some assumptions, but it usually, you usually can enable it. And then there is work in the compiler-based approach where we effectively move your data transfers and your kernel launches to earlier times and wait for them to finish at later times to overlap them with other things. That's the idea. Loop reorganization. So some people started to look at, I have multiple loops and like one for the teams, one for the parallel, but the one for the parallel has a lot of parallelism. The one for the teams doesn't. Can I kind of shift the parallelism onto the teams one so I can spawn more teams? Or one of the things we heard yesterday, sometimes it seems to be very helpful to collapse a couple of things, which probably goes into a similar direction. If your team's loop doesn't have enough parallelism, your distribute loop doesn't have enough parallelism, you're probably screwed. So we're looking at this. The main, this will only start once we change the way we do distribute workshare and SIMD loops in the GPU world. We're going to move the representation to make it easier to modify, analyze, and combine. So we're going to do that. Effectively, we're going to represent them as non-loops. We'll be fine. And then finally, last slide here, 3-level runtime. We heard that from Deepak as well. So we're working on the ways to let you control teams, parallel, and SIMD independently. You will get an advisor tool that will help you to make those decisions and find the right values and put the right things. Record and replay, I'm really looking forward to that. You run your application and you get basically an executable out of it where you can re-execute every kernel launch in isolation without having to rerun your entire application. You can run just the last kernel execution, for example. And then you can profile it and you can analyze it, or you also get the LLVM IR if you do LTO. You can fiddle with it. You can super optimize it, which is the next thing, and try to get the best performance just for this kernel launch. And then you at least get an idea where you are, like headroom and so on. Technically, you can also splice it back into your app, but we'll see. And I'm really looking forward to some smarts in the development environment in runtimes that, during development time and at runtime, actually, provide you with smart intel, that things that they tested, that is good, that they know, is actionable and so on. We have good ideas, but nothing yet. Pretty much it. And I'm out of time. Thank you.
All right. Thanks, Johannes. We have time for maybe one quick question, and then if folks are willing to stay a bit into lunch, we have a little bit more. Let's see, has anybody got a question to start us with?
You mentioned a number of options for LibOMP target for different levels of diagnostic information, debugging information, profiling information. Does that require a special build of libOMP target to get those, or that's by default you get those?
We got rid of all special builds. There's only a single build, and there will only be a single build in the future. Special builds is the worst.
Okay. The other question was regarding the OpenMP remarks. How does that work when you're having different programming models that are being compiled through this OpenMP backend? Is it still emitting OpenMP remarks for those, or?
Yes.
Okay.
So if we, for example, lower CUDA to OpenMP, OpenMP opt will still fire because we will do the lowering kind of early. We'll splice in the wrapper layer basically early. So the middle end will see, can't really distinguish that much, but we also, to support CUDA, we have extensions to the runtime. So it's not all of the middle end optimization are actually necessary or would trigger. So you might see some of them like OpenMP runtime call deduplication. We have part of the path knows which OpenMP runtime calls, like the literal underscore whatever, are kind of read-only and can be, or in what scope they can be deduplicated. It's like, oh, even though I have a lot of other code in between, I know inside of one function, this OMP getter will always return the same value. Domain knowledge. And they will trigger, and they're actually helpful for the CUDA part, for example, because we have to, in every wrapper part, like CUDA API 1, CUDA API 2, CUDA API 3, we might have to call the same OpenMP query functions to get information about the system. And then when we link it all together, the OpenMP op pass will just, simplify it.
All right. Well, one thing you mentioned, there's been a lot of improvements in JIT and LTO support.
Right.
There were some questions related to that for Deepak earlier. Can we be expecting LTO changes coming soon?
So I kind of alluded that device LTO will be default very soon for various reasons. And I think it will be the only way, with the caveat that you will be able to say, I do not want you to do actual optimization at link time. So just link it together. So you only, that will kind of give you non-optimized runtime code, or only partially optimized runtime code, which is not going to be great. So the argument against device LTO is going to be compile time. And that's roughly the only argument. And to counteract that, we're going to extend our linker wrapper that does the LTO to do a special parallel LTO step for device code, because device code, in contrast to host code, has nice properties usually. Host code is either one main function, so you have a single entry point and everything is reachable. So there is not it's hard to do cool parallel about that. Or it is a lot of entry points, like a runtime, where it's like, okay, and everything is kind of like intermingled, and I kind of have to show everything. So we have the nice situation that only the kernels basically are entry points, and there's kind of a few of them. So we can start to take the module, split it in parts, kind of one kernel at a time with its dependencies, with some sort of heuristic where to cut and where not to cut, and do that in parallel. And I think that will solve our compile time problems until we end up with so much GPU code that we'll have to see what else we do.
All right, that sounds pretty good. The other thing that you mentioned was multiple languages in the same compiles. Will the LTO play nice across different device runtimes in Clang?
No. I would very much recommend you do not mix code that requires a device runtime and then use different device runtimes. Like calling into a CUDA function compiled with CCE or with Clang from an OpenMP function of the other one is probably going to work just fine because they don't have conflicting device runtimes. Like the CUDA stuff is separate from the OpenMP stuff, but they should. I'm very certain that as soon as you have two OpenMP device runtimes into play, things go downhill fast. And I don't think we're going to support that. We'll just have to, if we want to support OpenMP from two different compilers, like CCA or AMD and LLVM and so on, we will have to find ways where you pick which device runtime you're going to use and that is going to be used. And I'm not sure we can or we want to, but that would be the only way I would do it.
All right. Well, thank you very much.